Welcome to the second video lecture on input-output subsystems. Before watching this video, please make sure that you have watched the first video lecture posted on this topic. Recall, in the previous video lecture, we talked about polling-based communication with IO devices. We saw that even the simplest IO devices have this abstraction of port, where each port essentially is a collection of four registers: the status register, the control register or the command register, the data in register, and the data out registers. So this picture over here shows a logical representation of an IO device, and these are our four registers that I was talking about. We saw in the previous lecture that in polling based communication, whenever CPU needs to communicate with an IO device, it will go read the status register of the IO device to check whether the device is available or not. If the device is busy, then the CPU will keep polling, or basically busy waiting on this status register until the device becomes available. When the device becomes available, the CPU will set up the device to execute its intended task, the read task or the write task, by setting up these other registers as appropriate and as necessary. And when the device is set up, it starts working on the read or write task. And in the meantime, the CPU keeps waiting again on this status register to detect when the request has finished. We talked about this polling based approach in details in the previous lecture, and from that discussion you will recall there were two important problems or limitations with this kind of polling based communication. The first problem was there is a lot of busy waiting here. So essentially CPU is spending a lot of time in a while loop, in an idle while loop, waiting for the device to become available. And when the device is available, the CPU has set it up to perform the read or the write operation. Then again the CPU is waiting in a while loop for the device to finish the job. So because of this busy waiting, the CPU is wasting a lot of precious cycles. It is not doing any other useful work in the meantime. And this is especially problematic if the IO device is much slower as compared to the CPU. The second problem was that we are only transferring one byte or one word of data at a time. How can we get rid of these limitations? In this lecture, we'll talk about a technique that will help us get rid of the busy waiting. And then we'll talk about transferring multiple words simultaneously in the next lecture. The main problem with the polling based IO is something like this. Let's say this is CPU, and let's say this is our IO device. We are executing some process P1 on the CPU, and let's say at this point this process P1 makes an IO request. So in the polling based IO, essentially once this IO request has been made, while this IO is being serviced, let's say from here to here, the CPU is not doing anything useful. It is essentially waiting for this IO request to finish, and only after it is done the processing or execution of process P1 can resume. So how can we better utilize this wasted time over here? A better and more efficient way of performing this IO operation would perhaps be something like this. Let's say this is our CPU, it is executing process P1, and here is our IO device. Let's say at this point the process makes an IO request. So what if instead of waiting for the IO device to finish, the CPU simply sets up the IO device, instructs it to, let's say, perform a certain input output operation, let's say read some data item X, and also instruct the IO device to inform the CPU once this reading is done. And then once this setup is done, the CPU goes back and it starts executing some other ready process on the ready queue, let's say process P2, and in parallel the IO device keeps working on this read command. At a later point, let's say over here, when the IO device is finished reading item X, it will inform the CPU. So this is the information. It will inform the CPU that the data item X is available, and when the CPU receives this information, it will suspend the currently executing process P2 and it will then go grab this data item X from the IO device and resume execution. This is the basic idea behind interrupt driven IO communication. So in this form of communication, instead of busy waiting or polling for the IO device to finish, the CPU simply sets up the IO device to complete the necessary task, and in the meantime it goes back and starts executing some other ready process. Later on, whenever the IO device is finished execution, it will inform the CPU. Now this inform is basically sending an interrupt. So the way to inform the CPU that a certain IO operation has finished is basically by sending an interrupt to the CPU. So later on, whenever this IO device is finished uh, performing the task, it will send an interrupt to the CPU to inform the CPU that the operation it had asked for has finished, the data is available. The way these interrupts are handled is, interrupts typically have a higher priority in our computer systems. So whenever an interrupt is received, the operating system suspends the currently executing process and goes on to service the interrupt. Now this slide over here briefly lists how this is done. We will go into many more details of this. So essentially the CPU will determine which device has caused the interrupt. It will then go on to service the interrupt depending on the device that has caused the interrupt. So let's say the CPU had made a read request to the device. It will go back and retrieve the data that from the device register, and then if there is more data that CPU wants to read from this register, from this device, then it will set up the device for more for the next read command. This picture over here summarizes the steps involved in an interrupt driven IO transfer. This will make more sense once we go through some details of implementing interrupts in our systems. Interrupts are defined as a change in the flow of a program that is external to the program. Let's try to understand why is that. Typically when a program executes, it executes sequentially. So right now let's say we are executing at program counter, then we'll next execute PC plus 1, PC plus 2, and so on. Let's say at PC plus 2 we encounter a branch instruction, let's say a BEZ instruction, and as a result of this, instead of going to PC plus 3, we may actually jump directly to, let's say, PC plus 10. Now this change in the flow of program was caused by the execution of this branch statement, which is internal to the program. This branch statement is part of the executing program itself. So this change in flow of program was not caused by something external. It was caused by the program instruction itself. As opposed to this, if you recall this picture from the previous slide, here when P2 has started executing, so P1 was the previous process, it made an IO request, and it was moved to the wait queue, and now the CPU has set up this IO device to, let's say, execute this read X command. At a later point, when this reading of X is finished, the IO device is going to send an interrupt to the CPU. P2 is executing at that time. When this interrupt is received, in response to this interrupt, P2 would be suspended and the CPU would start executing some interrupt handler. Now this change in the execution of P2 did not occur because of an instruction that P2 itself executed. This change has happened because of an external event. So that's why interrupts are changes in the flow of program which are external to the program itself. Typically, an interrupt is related to an IO event, as we have seen in this example on the previous slide. However, this interrupt mechanism is a very powerful framework in operating systems, and it is used by operating systems for other purposes as well. For instance, many operating systems use interrupt mechanisms for virtual memory paging as well. For example, page fault exceptions, they are raised as interrupts. You'll learn more about page faults and virtual memory in 5042. Similarly, system calls are also implemented based on interrupt based mechanism in our operating systems. However, in this lecture we are mostly going to focus on how interrupts are employed to service IO related events. If you look at the CPU, let's say this is our CPU, you'll find that there are several wires going in and coming out of this CPU. Two of these wires are of particular importance to us right now. So the first one is an interrupt line. This is the line that is used by an IO device to raise an interrupt or to interrupt the CPU. Once the CPU has received the interrupt and it is ready to serve the interrupt, it will acknowledge the interrupt on this interrupt acknowledgement line. So to interrupt the CPU, IO devices will assert a signal on this interrupt line, and the receipt of these interrupts would be acknowledged by a signal on this interrupt acknowledgement line. Typically, the IO devices will interrupt the CPU in one of these two situations. So first is, let's say the CPU had requested a write operation, and this write is now done. So when the write is complete, the IO device will inform the CPU that the write is done by sending an interrupt. That's one situation. The other possibility is, let's say it was a read operation and now the data is available with the IO device, so it is ready to transfer the data back to the CPU. That's another situation where the IO device will raise an interrupt. This slide over here summarizes the basic flow of how interrupts work. Whenever needed, an IO device will interrupt the CPU by triggering the CPU interrupt request line. When the CPU is ready, when it receives the interrupt, it is ready, it will acknowledge the interrupt, and then it will suspend the currently executing process to execute a special piece of code known as interrupt service routine or an interrupt handler to service the current interrupt. This is a high-level summary of how interrupts work. Let's now look at this process in many more details. Let's consider this example computer system for understanding the interrupts. This is our CPU. This is the main memory. This is the address bus. This is the data bus. Then we have an interrupt line. So this line over here, this is the interrupt line. This is the line where an IO device would assert a signal if it wants to interrupt the CPU. Once the CPU has received the interrupt and it is ready to service the interrupt, the CPU will acknowledge the interrupt on this line. This is the interrupt acknowledgement line. And here are several IO devices that are connected to the CPU. There is a special table which is loaded in the kernel address space in the main memory. It is known as the interrupt vector table. We'll come back to this table a little later in this example. As a first step, let's assume that a certain IO device needs to interrupt the processor. So it will basically assert a signal on the interrupt line, which is basically this line over here. So it will assert a signal on this line, this interrupt line, to interrupt the CPU. Once the CPU has received the interrupt and it is ready to serve the interrupt, it will acknowledge the interrupt on this interrupt acknowledgement line, this line. Note that there is only one interrupt line, and there are so many different IO devices that might be connected to the computer. Any IO device that needs to interrupt the CPU would use the same interrupt line to assert its signal or to send the interrupt. So the question is, how would the CPU know which of these several IO devices has caused the interrupt? The way this identification is done is, once the IO device that had caused the interrupt, once it sees or receives an acknowledgement on this interrupt acknowledgement line, it will put a small integer on the system bus, right? This small integer is known as an interrupt vector, and the goal of this integer is to identify the device. So essentially, the IO device will put a small integer on this data bus or this system bus to identify itself. Let's assume this was the IO device that had caused the interrupt. So to identify itself, it places a small interrupt vector and small integer on the data bus. Let's say here in this case the data vector or the small integer is, that interrupt vector is 10. On seeing this interrupt vector on the data bus, the CPU will basically save this interrupt vector, this identifying information, for later use. So far we have seen that the CPU received an interrupt, it acknowledged the interrupt, and it is now ready to serve the interrupt. In order to serve the interrupt, essentially the CPU needs to execute a special piece of code known as interrupt handler. Depending on what device has raised the interrupt, what kind of interrupt has been received, a different interrupt handler code would need to be executed. But also recall, typically these interrupts come from the IO subsystem, and when an interrupt arrives, it is very likely that the CPU was already in the middle of executing some other process. So let's say the CPU is executing this other process and it is somewhere in between. This is where it is executing right now. So in order to serve the interrupt, the CPU would first need to suspend this currently executing process. Essentially, we do not want to throw away all the work that this process has done so far. When we restart or resume this process at a later point, we would want to resume it from the point where it has left off. So for example, if it has executed until this point PC, we would want to restart it from here PC plus 1. So in order to be able to do that, before suspending this process, we would like to save all the information which is needed to resume its execution from where it is leaving. So we'll save information like the current value of program counter, the current state of the register file, and so forth, right? This process is very similar to what we have seen in the context switch earlier in the operating system. So all of this information would be saved in the memory, perhaps in the process control block of the executing process. This executing process, after being suspended, would be moved back to the ready queue, and now the CPU is ready to execute the desired interrupt handler. We are now ready to run the interrupt handler, and like we have seen, depending on what IO device has caused or raised the interrupt, a different interrupt handling subroutine may need to be executed to interact with the IO device. For example, the code that we need to run to retrieve the data from the keyboard is different from the code that we need to run to retrieve the data from the hard disk. Similarly, the logic that we need to write the data into the hard disk is different from logic that is needed to write the data on the computer screen. So typically, along with the interrupt handler, the corresponding device driver of the IO device is also executed. Some code from that device driver is also executed. Interrupt handler is part of the kernel address space. There is an interrupt handler for every type of interrupt that may be raised in our computers. Here are some examples. Let's say we have an interrupt handler here. This is a keyboard interrupt handler to handle interrupts coming from the keyboard. Here we have a mouse interrupt handler to handle interrupts coming from the mouse. Similarly, this is a hard disk interrupt handler to handle interrupts coming from the hard disk, and so forth. So if there is an interrupt coming from the mouse, we'll have to invoke this particular interrupt handler. Similarly, for keyboard interrupts, we'll need to invoke this particular interrupt. Now the question is, given so many interrupt handlers, there might be hundreds of interrupt handlers in the kernel address space. So given all of these interrupt handlers, how would the CPU know which of these hundreds of handlers need to be invoked to service the current interrupt? And this is where this interrupt vector table comes in. Think of this interrupt vector table as a table that contains addresses of all of these interrupt handlers. Let's assume this keyboard handler, this starts at address hexadecimal, let's say 1234. This mouse interrupt handler starts at, let's say, address 4321. Let's say this hard disk handler starts at address A123, and so forth. So in this interrupt vector table, you will have, let's say, in the mouse entry, let's say this is the entry for keyboard. Let's say you will have the address hexadecimal 1234 here. This is the starting address of the keyboard's interrupt handler. Similarly, for mouse, you'll have an entry of this address hexadecimal 4321. For this hard disk, you'll have an entry hexadecimal A123, and so on. And a very nice thing about this table is you don't really need to search in this table for the address of the interrupt handler that you're looking for. Recall the interrupt vector that is placed by an IO device on the data bus to identify itself. This table is actually arranged according to the interrupt vector or vectors of the IO devices. For example, let's say this is mouse. Let's say the interrupt vector or the identifying integer for this mouse is, let's say, 10. Similarly, let's say this device 2 is your hard disk, and let's say the identifying information for this hard disk, the interrupt vector for this hard disk is 11. So the address of the mouse interrupt handler would be stored at the 10th as a 10th entry in this interrupt vector table. Similarly, the address of the interrupt handler for this hard disk would be stored as the 11th entry in this table. So the CPU doesn't need to really go through all of these entries. It just recall that we are saving this interrupt vector information that was placed by the IO device. The CPU had saved this temporarily. Now it was saved for this purpose. At this point, the CPU will simply it will retrieve this interrupt vector and directly jump to that particular location. Let's say the vector was 10, so it will directly jump to this 10th entry and read the address here, and then it knows where the interrupt handler to handle this interrupt coming from the mouse is located. So it will directly jump to this address hexadecimal 4321 and start executing the code over here. This is how the interrupt handler is located and invoked for execution. We have already seen on the previous slide that after locating the interrupt handler, the CPU will jump to the interrupt service routine, execute it to service the interrupt. Note that different interrupt vectors, basically the interrupts corresponding to different IO devices or different types of interrupts, will jump to different interrupt service routines or interrupt handlers, in other words, as we have seen. Now that interrupt has been served, we have taken care of the interrupt from the IO device. It is time to resume the execution of the process that was suspended for executing the interrupt handler. To do that, some architectures provide a special return from interrupt instruction. This instruction basically restores the saved values of the program counter and other system registers that we had saved earlier while suspending the previously executing process, and it will then resume the execution of that program from where it had left off. So here is a quick summary of what all the interrupt service routine does. So first of all, for the currently executing process which needs to be suspended or preempted, the interrupt service routine will save all the state of its registers, the program counter, and so forth, of basically all the information which is needed to resume its execution from the same point at a later point in time. Next, it will execute the IO device code, which will include code from the device driver. Once the interrupt has been handled, the interrupt service routine will restore the state of registers so that the originally executing process can be resumed, and finally we'll return to the execution of the original process wherever it left off. Although we went through detailed steps for an example showing how an interrupt is handled in our systems, we went through a relatively simple example where there was only one interrupt. However, in modern computer systems, there are hundreds and thousands of interrupts per second. So there is nothing stopping from multiple interrupts arriving at the same time. It is also possible that we are serving one interrupt and even before it is finished, another one arrives. So the question is, how do we handle multiple interrupts simultaneously? There are many ways of doing this. One simple, easiest way is always serve interrupts in strictly FCFS order, first come, first serve. So once we have started serving an interrupt, any new interrupts that arrive, they would be queued, and the interrupts would always be served in the arrival order. So advantage of doing this is it is very simple to implement. Another advantage is it is fair in the sense that interrupts are serviced in the arrival order. so there is no starvation problem. However, there is a practical problem associated with this scheme, and the problem is these interrupts are usually coming from the IO devices, and different IO devices have different delay tolerance. On one hand, we may have a sophisticated IO device, for example a hard disk, that has, let's say, a large buffer on board. So even if the CPU doesn't collect the data which the hard disk has immediately, its buffer has enough room to store the data for a while. As opposed to this, there might be a very simple sensor, which is, let's say, a temperature sensor or some other kind of monitoring sensor, which has very small buffer space. So if the CPU does not collect the data from this sensor immediately, the data may be lost because it would be overwritten by the next data input that is coming, or basically the next data point that the sensor is collecting. Therefore, it is important that the interrupts that are coming from such devices that have low delay tolerance, they get a higher preference, because there is a danger of losing the data. And this FCFS policy is not going to work well for this setting. Therefore, another way of handling multiple simultaneous interrupts is by prioritizing them. We will assign priorities to different interrupts depending on their importance and also delay tolerance associated with the device. So the way this would work is, let's say an interrupt is being processed and a new lower priority interrupt comes in. So any lower priority interrupts would simply be queued. The CPU would not be interrupted. The interrupt processing will continue as it is. However, if we are processing an interrupt and let's say a higher priority interrupt comes in this case the CPU would be interrupted a second time. The interrupt that is being served currently, it would be suspended and the higher priority interrupt would begin service. Based on that description, you might imagine that we would need a lot of priority levels for the interrupts. Perhaps we need a priority level corresponding to every type of IO device that might be connected to the computer. But that is not how most processors implement interrupts today. In most modern CPUs, there is actually only two priority levels supported for the interrupts. So there is maskable interrupts and non-maskable interrupts. Maskable interrupts are those interrupts which can be disabled by the CPU during some critical processing if needed. As opposed to this, non-maskable interrupts are those interrupts which cannot be disabled by the CPU, and the non-maskable interrupts are basically used for reporting events, almost catastrophic events, for example some kind of hardware failure in the system or maybe some kind of unrecoverable memory error. The IO devices that are connected to the computer system, they all use this maskable interrupt. So essentially all the IO devices are mapped onto this single priority level, maskable. Hence, in modern computer systems, there is typically an external interrupt controller which is used to distinguish between the priority levels of different interrupts. By default, the CPU is only supporting these two interrupt levels, and out of these two, the IO devices have to use this maskable level from the CPU's perspective. Another issue that we need to discuss with respect to interrupts is, sometimes when the processor is executing some critical piece of code, we may need to disable the interrupts. So for example, let's say there is a piece of code, let's say that we have this code, it has several lines, and let's say out of these 3 lines, 3, 4 and 5, they need to be executed for some reason without any interruption. So once we start executing this instruction 3, we cannot for some reason interrupt or break the execution of this code until we have finished executing instruction 5. So to ensure such critical processing, it is important that before we start executing this instruction number 3, we disable all the interrupts. The interrupts would be enabled again after executing this instruction 5. So from instruction 6 onward over here. You would realize at this point, if we do not disable the interrupts and let's say we start executing instruction 3, so let's say we execute instruction 3 and while we are at instruction 4, there is an interrupt that arrives. So whenever there is an interrupt, the currently executing process is suspended, right? So this will actually break the requirement that instructions 3, 4 and 5 had to execute without any break. That is why disabling the interrupt for such critical processing is important. You should realize not all the interrupts can be disabled. We talked about maskable and non-maskable interrupts. So maskable interrupts are those interrupts that can be disabled. As opposed to this, the non-maskable interrupts, they cannot be disabled. When we support interrupts in our processors, it also affects how we execute instructions in our pipelines. Recall this three-stage pipeline that we talked about earlier in the course. So let's imagine that we have this three-stage pipeline with fetch, decode and execute stages. In our previous discussion, we saw that at any point in time there could be up to 3 different instructions in these 3 different stages, right? So for example, let's say instruction 3 is in fetch stage, instruction 2 is in the decode stage, and let's say instruction 1 is in the execute stage. Previously we have seen that as soon as this instruction 1 finishes, it graduates out of the pipeline. Instruction 2 will move to the execute stage, instruction 3 will move to the decode stage, and instruction 4 can start fetching. However, if we have interrupts in our processors, we cannot directly start fetching instruction 4. Before fetching any new instruction, we should always check whether there is an outstanding interrupt or not. If there is no outstanding interrupt, then we can proceed to fetching the next instruction as usual. However, if there is an outstanding interrupt, then we cannot fetch the next instruction from the currently executing process. We need to jump to the interrupt handler. We basically need to start executing the interrupt handler. Alright, so finally, before closing the page on interrupts, let's quickly think about advantages and disadvantages of interrupt-driven IO. So we have seen that in interrupt-based IO, the CPU does not have to busy wait for the IO device to finish processing. It can simply set up the IO device to do or execute a certain command, and then CPU can go off to do some other useful work. For example, execute some other ready process from the ready queue. So it saves a lot of time as with respect to the polling based IO. Another important advantage is this interrupt driven IO is a very generic framework which can easily be modified or extended to accommodate hardware changes. So for example, let's say there is a new IO device that is introduced. All we need to do in order to integrate that IO device into our computer systems is write a new device driver and make a new entry for this IO device in our interrupt vector table for its corresponding interrupt handler. So it's a very generic and powerful framework. And like we have seen earlier, interrupt based mechanism, this interrupt mechanism in our systems is used not only for communicating with the IO devices, but also for providing some other services, for example handling traps and exceptions. So traps is basically associated with supporting system calls. We'll talk more about traps and these exceptions in the next lecture. So there are several advantages as you can see, but there are also some key disadvantages. One important disadvantage is, although interrupt driven IO saves time with respect to polling based communication, the CPU is still heavily involved in the IO operations. So note that for every word that is being transferred, the CPU will have to go set up the IO device, and then it will come back and start executing some other process. When the IO device is done, it will send an interrupt. On receiving the interrupt, the CPU will suspend the currently executing process. It will go gather the data from the IO device, let's say, and then set the IO device to transfer next byte or next word. Then again CPU goes back, and this process is repeated for every word that the CPU needs to transfer. So if the CPU needs to transfer, let's say, thousands of bytes or thousands of words, there will be thousands of such context switches. So every time there is an interrupt, we need to do this context switch. We have to suspend the executing process, we have to invoke the interrupt service routine, and so forth. So this is a lot of overhead involved with every byte or word transfer. In the next lecture, we'll talk about an IO technique called direct memory access, and we will see how the DMA transfers can eliminate these so many context switches and interrupts for every byte transfer. Finally, related to the previous one, again there is a, although IO, the interrupt based IO is a very powerful mechanism, it is still complex and there is a lot of overhead associated with the suspending and resuming the programs. I hope that was helpful. Please let me know if you have any questions. Thank you.